So we are starting the last chapter that we will do in AP Calculus, and I have to tell you, it's my favorite chapter. I'm sure you think that all of the chapters are my favorite, which they are, but this one's the most favorite. So we're going to start with something that it's going to seem pretty easy compared to the stuff that we've done so far, and then 6.2, 6.3, 6.4 are definitely more on the brand new side. So 6.1 is area between two curves. We've seen area under a curve, but the bottom marker is always the x-axis. It's always in between a curve and the x-axis. So we've kind of sort of done this already. It's just that our other curve is always y equals 0, aka the x-axis. All right, so like I said, extending that application to going between two curves. So I'm going to start you off with a picture. So what I want you to do is draw just a pretty generic picture here. So if we look at the first quadrant, I want you to draw an upside down parabola and a right side up parabola. It does not have to look exactly like mine, believe me, it's not important. So they intersect right here and right here. We're going to call this point right here A, and then we'll call this point right here B. And then if we say that this upper function right here is f of x, and this lower function right here is g of x, we're going to carry this picture throughout. And so I've actually given you the formula already, but I kind of want to give you a picture representation of why exactly it works out the way it does. All right, so here's the area that we're trying to find, the area that I'm going to shade in pink here. All right, I'm not very good at coloring the lines. But that's what we're looking for, the area in between the two curves. And so the formula that I've given right down here, all we're doing is we take f of x, which is the upper function, and we subtract g of x, which is the lower function. Okay, so here we'll hopefully make it make sense. So if we take, okay, so now I want you to draw the same picture. I mean, make it as similar as you can. It doesn't have to be absolutely flawless. Okay, so if this again is f of x, if we say this is A and this is B, what we're first doing, remember properties of integrals, we can split this up into two separate pieces. So really it's like we're taking the integral of f, and the integral of f represents the area under f, all the way down to the x-axis. So that is this region that I'm about to shade right here. So from f of x all the way under. So if we're trying to find this region, what we do is we take this region, this whole region that I just shaded in, all the way under f of x, and we subtract this part of it right here, which is the part that's just under g of x. So it's this, and then minus this area right here, so minus the area of g of x. Okay, and again, that same drawing doesn't have to be flawless. So there's A, there's B, this lower one is g of x, and so what we're subtracting away is the part underneath, the part that's not in between the two curves. Okay, so if we start with this overall pink area and subtract away this smaller pink area, what we end up with is the part in the middle. And so basically the overall gist that we're doing is we're taking the area under the upper curve and then subtracting the area underneath the lower curve, which leaves you just with the area in between. So this right here is the formula that we're going to be using every single time that we do area between the curve problems. So just to make it super official down here, f and g have to be continuous. You know, that's pretty much an assumption that we make with most of the things that we do in calc. We want g of x to be less than or equal to f of x for an entire interval. Obviously, there's going to be 2 points, at least 2 points where they'll be equal, and those will be the endpoints of our interval. But other than that, g of x has to be below f of x for all x in this interval. Then the area bounded above by f and below by g, and then the vertical lines a and b, those are your markers right here on the left and right hand side, is, so we use a for area, and it is just equal to what I wrote up above here. Okay, so here is something that is super, super, super important to remember. If you've got this formula, all you need to remember is that it's going to be the upper function minus the lower function. Okay, every single time, because we mentioned in here that g is smaller than f, which makes f the upper function, and it's always going to be f minus g. So upper minus lower every time. Otherwise, you would get the opposite of what you're looking for. All right, so example 1. You'll notice in these notes that I included little coordinate systems. I need to see a sketch for every single one of these. if you're thinking, why do I need a sketch? I can just plug it into my calculator or something. The only way you can know which function is above and which function is below is if you give me a sketch. And the more in-depth we get into chapter 6, the more important it will be that you've got a picture of the area in front of you. So I need to see a sketch. That will be worth points when we take a test. Okay, so sketch the area bounded by this graph right here, on the left by 0, and on the right by 2. Okay, so I'm going to start with this function right here, x squared plus 3. So we should have enough knowledge of functions to at least be able to sketch these. So this is a parabola. It's centered on the y-axis, and it has a y-intercept of 3. So it looks like this. And then I know if it's just an x squared, my next points are going to be right there. Okay, so sketch that out. There's my parabola. Okay, so I've got that. That's f. And then 1 minus x, so I have a y-intercept of 1, and then it's got a slope of -1. So I just kind of continue on with my slope of -1 all the way down here, so I'm going through all those corners. So there's that one, and then it says bounded to the left by x equals 0, so that's a vertical line right here, and then on the right by x equals 2. All right, so there will be 4 lines that you're going to be talking about here, and it gives you a shape in between. And so I'm going to need to see a picture, and I'm going to need to see the shape shaded. Otherwise, I will not give you credit for homework. I will take off points on tests. All right, so that's the area that we are trying to find. The left bound and the right bound become your bounds of integration, the a and the b. And so when we're looking for our area, we've got a equals, and we set this up, we're going from 0 to 2. And we always take our upper function, and you need to put it in parentheses because subtraction will mess with your signs otherwise, and then minus the lower function, which is this linear function, and that's 1 minus x. Again, careful with parentheses. If you didn't have parentheses here, we'd forget to add x instead of subtracting. Don't forget your dx. Okay, so let's simplify that up and then do the fundamental theorem. Okay, so x squared plus x plus 2. All right, that's what we get when we start to simplify that down. So let's take our antiderivative. So we've got 1/3 x cubed plus 1/2 x squared, and then plus 2x. And we're going to evaluate that from 0 to 2. 0 is easy because we know when we plug in 0, we get 0. So first we plug in the 2, so we get 1/3 times 8 plus 1/2 times 4 plus 2 times 2, and then just minus 0. So this is going to be 6. 6 plus 8/3 would be 18/3 plus 8/3, and that is 26/3. For the most part, I would say probably 80% of the time, questions like this are going to appear on the calculator section of the AP test, which means all you need to do is write this down. You'll get a point for the bounds, you'll get a point for the setup, and then you can just plug it into your calculator and give the answer. So, while it is super, super important to be able to integrate by hand, and I'm going to make sure that throughout this chapter we still have a handful of problems where we are integrating by hand, for the rest of these notes, and then in the future, in this chapter, I'm going to do a couple of them by hand, and then we'll just start showing you what the setup looks like and how to just plug it into your calculator, because the actual integration was part of a previous chapter. This chapter is all about how to set up these integrands and what it looks like when you're subtracting upper minus lower and everything like that. Okay, quick little note here that's going to lead us on to the next page. In this example, these graphs don't intersect. All right, they're never going to intersect. The values of A and B were given to you. Most of the time, it'll just say, hey, find the area between these two curves, and it'd be something like f and g that I drew up above, and the way you find your bounds is by figuring out where they intersect. So you're going to have a little bit of algebra work to do first to figure out where the functions intersect, and then you set that up as your bounds. All right, so let's look at our next example, example 2. We're going to start with a graph, and the easiest way to get accuracy on the graph is to find the intersection points first. So we need to figure out where those two graphs intersect each other. So for our intersection points, we are going to set them equal to each other. So we're going to take negative x squared plus 4x plus 2 and set it equal to x plus 2. I would just move everything over to the right because this is a negative x squared. So if we move everything over, I'll be left with a 0. If I add the x squared over, subtract the 4x, and then subtract the 2's and they'll cancel. If I factor this down, then I know they're going to intersect at x equals 0 and x equals 3. That's only half of the intersection point. Remember, that's just the x value. You still need to know the y value. So plug it into the simpler of the two functions. So I would plug it in here. So we know they're going to intersect at the point 0, 2. It's that point right there. And then if I plug in 3, they're going to intersect at the point 3, 5. Okay, so that's right there. And then we sketch our graphs from that point. Again, like I said, the big part is knowing which one's above and which one's below. So we know what the line looks like. The line is a linear function, slope of 1, that goes through these points, and we can keep drawing it right through the corners. All right, so that's our linear function. That's x plus 2. And then our parabola could either go like this, or it could go like this, and that is all dependent on the negative x squared. The fact that it's a negative x squared tells us that it's going to be upside down, concave down. All right, so just sketch it in real quick. Doesn't matter exactly where the vertex is. Like I said, the important part is that we know the parabola is above the linear function. So I need to see this. I need to see the precise points where they intersect, and I need to see you shade in the region that we're finding the area of. Okay, so all those things in order to get full credit. So now from that point, once the setup is done, because the setup is the more difficult part. Like I said, I know you know how to integrate, or I hope you know how to integrate. So from this point in these notes, we're just going to set up the actual integral and then just plug it right into our calculators. So the integral from, we start at x equals 0, and we end when x equals 3. Okay, so those are our bounds. And then we put upper function, which is negative x squared plus 4x plus 2, and then minus the lower function. Make sure you're putting it in parentheses, otherwise we could mess up our signs, and don't forget your dx. Okay, so now we're going to plug it into our calculator. So on the Inspire, we are going to hit the menu key, and then there's this whole calculus menu, and we're going to do a numerical integral. Okay, so I'm going to go from 0 up to 3. Be careful with your parentheses. So we've got negative x squared plus 4x plus 2, close the parentheses, minus, open up a new set of parentheses for the x plus 2, close, close, and, oops, that one was unnecessary, dx. Okay, 4.5. We can do 4.5, we can do 9 halves, we can do 4.5, whatever. Okay, so that's our final answer. I, of course, have my 84 at home, but you would press the math key, and then you would do, I believe it's number 9. It's either 8 or 9. I'm going to bet on 9. And then you should all be updated like this, and so we're going to type in the lower bound and the upper bound, and then just plug this exact thing in. If you're one of the few people that has the 83 and you don't have the updated system, what you do is you are going to plug in the integrand first. So all it'll say is fn int, and then it'll open parentheses. You are going to type in the entire integrand, this whole quantity, comma. Then you're going to type in an x, because that's our variable, comma. Then a 0, comma, 3, and then close the parentheses. And that should still give you the 4.5. So I'm sorry, but I know there are a couple of you that have the 83 that doesn't have the updated operating system. Okay? This one, this is a function that's given as x equals, and it's all in terms of y. Okay, and since we've got so much going on with the y over here, it would be impossible to actually get the y by itself. So we are going to keep it as a function of x in terms of y, and all of this will change. These will become y bounds instead of x bounds, and this will be a dy, and the whole integrand will be written in terms of y, which we can do. We can absolutely do that. The weird part is that we usually don't know what these graphs look like. Okay, so we're going to start with the ones that we do know, which is the vertical line and the horizontal line. So I want us to start with this, the line x equals 0, and then the line y equals 3. Okay, so we've got those. So that's going to be part of our graph that we're drawing. And then this guy right here, what we're going to do just to kind of help us out is we can set it equal to 0 to see where it's going to intersect, and then maybe just get a couple more points by plugging in some different values. All right. So if we set it equal to 0 for x, so we can do 0 equals okay, so we know the only time this is going to happen is when y is equal to 0. So it's going to intersect right here at the origin. We've got that going for us. And then we could try to figure out where it's going to intersect this line. We could do that too. So if we see where is it going to intersect this line, so we could plug in a 3. That would work. So x equals 3 over square root of 16 minus 9. And so that is a nice 3 over root 7, which will at least give us an approximation. Okay, so 3 divided by root 7. And there are so many different ways that you could do this. I'm just giving you some tips. This is about 1.134. Okay, so that would be this value right here. So when y is 3, x is like right about here, just past 1. Okay, so that's 1 point. And then what I would do is maybe plug in some different values for y. So if we plug in y equals 0, we know we get 0. I'm trying to think of what else we could plug in to make this kind of nice. We could plug in y equals 1. We could plug in y equals 2. Let's plug in y equals 1. Okay, so 1 divided by the square root of 15 gives us about 0.258. And so when y is 1, x is 0.28, so that's going to be like right here. And then we can play around with just a couple little pieces, like we could plug in a -1. If we plug in -1, we get x equals negative 0.28, because that was out of a -1 over 50, or root 15. All right, so we could have another point right here, and all these points actually end up being symmetric. So like this point right here would transfer down to this point right here. And what ends up happening is it looks something like this. All right, so something like that. Kind of a weird looking shape there. We do have these 2 horizontal asymptotes, and that's because if you look at the denominator here, if you plugged in 4, it would be a denominator of 0, which would make it undefined. And so that's why we have horizontal asymptotes at 4 and -4. So it looks like that. The little part that got closed off is actually just this teeny little sliver in here that got closed off by the y-axis, the line y equals 3, and then this weird looking curve. Okay, so that's what we're dealing with. Remember, everything is going to be in terms of y instead of in terms of x. So the area is going to be equal to, and then we take the integral from, we start at y equals 0 and end at y equals 3. And then this time, all right, so we're going to make a little note about this. When we're dealing with y's instead of x's, instead of doing the upper function minus the lower function, we do the right function minus the left function. You're always doing the one that's in the more positive region minus the one that's in the less positive region, just like we are up here. These are the larger values of x minus the the larger values of y minus the smaller values of y. These are the larger values of x minus the smaller values of x. So when we are dealing with stuff in terms of y, we are always, always, always going to do right minus left. Okay, so the right function is that weird curve, that y divided by the square root of 16 minus y squared, and then minus the function on the left, which is technically just the y-axis, which is 0. Okay, so now this, you should be capable of doing this by hand. People may think inverse sine, but it's not. It's a substitution because I have a y in the numerator. So I would make a substitution for 16 minus y squared, and then end up balancing out the constants to take care of that y. But like I said, the more important part is being able to set these up. So let's type this in. We've got menu. I'm going to take the calc menu, numerical integral. And I'm going to go from 0 to 3. Your variable doesn't matter, especially if you're on an 84. You might just want to use x every time. But I could use y since I've got a full alphabet pad on the Inspire. Just make sure if you do choose y, you make this a dy. Otherwise your answer would be wrong. Okay, so that is our approximation. It's about 1.354. You need that 3-digit accuracy. You'd get the answer wrong on the AP test if you didn't have 3-digit accuracy. Okay, last problem in the set of notes. Sometimes curves will crisscross over each other. Picture if you had like a cubic function and a parabola, which I think is exactly, yep, it's exactly what we have here. They're not always nice and neat. Like, hey, it crosses here, and then it crosses here, and then it never comes back up. But picture if you had something cubic. It could go up, come down, come back up. What happens in those cases is that there isn't one function that's always the upper function, and there isn't one function that's always the lower function. They're going to crisscross. And so if they crisscross, what we need to do is actually set up 2 separate integrals. Okay, so we're going to start by finding the intersection points. Okay, so we're going to set 3x cubed minus x squared minus 10x. We're going to set that equal to the other curve, a negative x squared plus 2x. We're going to move all the stuff over to the left-hand side there, so we've got 3x cubed. The negative x squareds actually end up canceling out because I've got 1 on each side. And if I subtract the 2x, I have 12x. Okay, I'm going to factor out a 3x. And I'm left with x squared minus 4. And so that gives me 3 intersection points. I have x equals 0, I have x equals 2, and I have x equals negative 2. Okay, so those are the x values. Then I'm going to plug the x values into either one of these equations and get my y value. Okay, so if I plug in 0, that's easy enough. I'm going to get 0. So they're going to intersect each other at the origin. If I plug in 2, I'll have a negative 4 plus 4, which again is 0. So they intersect right here. Then when I plug in negative 2, I get a negative 4 minus 4. So that actually goes down to negative 8. So I'm going to have to extend this a little bit. So here's negative 5, 6, 7, 8 right here. Okay, so here's what they look like. This is a negative parabola. So it's going to go through this point. It's going to come up, go just a little bit higher than this, and then come back down, symmetric on both sides. So that's our parabola, that's g of x. Our cubic function, because this is a positive x squared, it looks just like the original cubic function, so it starts at the bottom and then works its way to the top. So what this does is actually kind of weird. It starts here, it goes up through this point, comes down through this point, turns around again in here, and then goes up like that. Okay, you could graph these for sure. I'm just kind of showing you what I would expect you to know about these graphs. Once you have the intersection points, it doesn't matter, how high this point is or how low this point is. It just matters which one's on top and which one's on bottom. So it is these 2 pieces that we're looking for here. They're 2 separate pieces. The reason we count them as 2 separate pieces, again, is because on this half, the cubic is above and the parabola is below, but on this half, the parabola is above and the cubic is below. So we're going to set up one last definite integral here. So the area, we have to break it into 2 pieces because they're crisscrossing. So from negative 2 to to 0, those are our x values. The cubic function is up above. So I do the cubic function in parentheses minus the parabola. Don't forget your dx. That's going to give me the first half, this long, narrow piece. And then plus, then we pick up at 0 and go to 2. And from x equals 0 to x equals 2, the quadratic is actually on top. So I put upper minus lower. And again, since the upper and lower change positions, I have to set up 2 different integrals. Otherwise, I would get the wrong answer. Okay, so this whole strand, you can actually plug that whole thing right into your calculator, and I will show you how. So either menu 4, 2, or math 9, if you've got an 83 or an 84. So we're going to go from negative 2 to 0. In parentheses, I've got 3x cubed minus x squared minus 10x. Close the parentheses, minus parentheses, negative x squared plus 2x, parentheses, dx, and then I can keep it all in one line. Plus, whoops, no, not in there. Here, plus, sorry, menu 4, 2, and then I'm going from 0 to positive 2. First set of parentheses has my quadratic, close, minus, and the second set of parentheses has my cubic, because it's below during that interval. Okay, close parentheses, and dx. All right, so we should get 24. Just a nice, neat answer there. All right, so that is a 24. All right, so that covers it. We've got some AP problems that we can talk about in class, and get ready to do some of these practice problems.